Hi, and welcome to a video about numbers, about physics, and how they apply to biomedical engineering. This is week 2 of our course. I'm going to assume you've gone through the textbook, at least chapter 1 of the textbook, and have some idea of what it says in there. And we're going to build on that, dive down into some topics, and hopefully motivate you to understand why physics is really important for biomedical engineering. The examples I like to show are ones that come out of daily life in some regards. And when I first started teaching this particular course 5 or 6 years ago, I was riding into my first class and I got stung by a wasp. And you can see the picture here of my lip all swollen up. And that started me thinking, how did the physics of that work? How could the wasp fly into my face as I was riding down the hill on my bicycle, somehow move its body around, turn its stinger, which is at the far end, and sting me? How does it fly? What's the aerodynamics of a small insect like a wasp? And how do they actually deliver the poison? What is the effect of that poison on me? Why does my lip swell up? There are all kinds of questions that naturally came out of that encounter that started me thinking. And so I spent some time talking about that. A couple of years later, we were having the very first week of class. In fact, one of the very lectures during that week was during the total solar eclipse. And so it was natural to talk about that in the context of physics, the physics of light, the way light interacts with our retina, our eye, how we perceive vision, how light can do damage to our eye. These are all physical phenomenon that we really need to understand if we want to understand the life that goes on around us as biomedical engineers. And then in 2018, there was this big story that came out the week before class started, in which there was some initial data, initial results from a lab suggesting that certain hearts of neonatal pigs in this case, could actually recover from a heart attack. Now, neonatal pigs don't usually have heart attacks, of course, but they were induced in an experiment, and the hearts actually recovered. Now, this is breakthrough thinking because for a long time, we always believed that hearts die for good, that when you have a heart attack and there's not enough blood going to your cells, those cells will die and they will form a scar, and you'll live with that scar for the rest of your life. And that scar affects all kinds of behavior of the heart. And so this was a really radical thought, and we spent some time talking about what the consequences of that would be. Last year, we also got into the domain of regulation of the heart through external electric fields. Now, that's a defibrillator is the extreme example of that, and we'll come back to defibrillators. But this is the notion that by modulating the behavior of the heart, you can actually improve the heart's performance and reduce some of the risks of abnormal heart rhythms. And that was, again, a breakthrough idea that last year was reflected in a new device that was receiving FDA evaluation and approval to actually modulate the heart. And these would be implantable devices, like a lot of modulators. You might have heard about modulation of the brain. That's another very hot topic in our department, actually. But this was a modulator of the heart, so quite different, really, in obvious regards. Also, now 2 years ago, a former student of ours, former student of mine, a PhD student of mine, who you see in this photograph with the big arrow, you can't quite see his face, he received a clearance for the device, and then this past year, or 2018 actually, they first had their IPO, their initial public offering, so they went public as a company, raised $100 million on the spot, on top of the investment they'd had over the years. And they had a device that didn't modulate the heart. It actually modulated a nerve that controls the tongue, which controls breathing when we sleep. And the goal of this device was to treat sleep apnea. So this is a condition that affects lots of people, especially as they get a little bit older, and results in constant waking, because they're not getting oxygen, so their air passage, their airway closes down, because that muscle isn't stimulating, because the tongue falls back on the vocal cords and into the back of the mouth, blocks the air, and then eventually, of course, we wake up because we're not getting air. That's what our body does. But this year, I want to go a little deeper into an example that I've looked at before, but being at home so much this last summer, I love to watch the hummingbirds. They sit outside in our hummingbird studio. I've shown you a picture of that before, a little video of that. So in a hummingbird studio, we have a hummingbird feeder and our dinner table. So we eat dinner, we watch the hummingbirds. So they're fascinating birds. I hope you've had some time in your life to watch them. There are lots of them in Utah. They're easy to attract. And we're just amazed by the ability they have, the flying ability they have, the hovering ability they have. They can fly forwards, backwards, and still. And so we're fascinated in some regards by just that behavior, just that ability to jump up and hover and stay in one place, and then to be able to maneuver very precisely as they're hovering. Of course, they come around to a feeder in order to get liquid. The more interesting behaviors we've seen is when there's multiple hummingbirds, and they will battle, they will look at each other, gauge each other, figure out some dynamic, and sometimes, but not very often, two of them will actually sit on the feeder at once and not fight with each other because their competition for food is fierce. They have amazing metabolism. They have incredible metabolic and food needs to drive that metabolism. They eat half their weight every day in nectar just to keep doing what they're doing. They have incredibly high and variable heart rates. There's all kinds of incredible physiology we could get into, but I wanted to focus in this case a little more on their flying behavior. And so I dug into the literature, and sure enough, there are studies on hummingbirds and how they fly. I'm not the only one to be fascinated by this. And so this is just one example of a study I found. You can find a reasonably rich literature on this if you go searching in Google Scholar, let's say. And this team set up a flying pen, if you will, for the hummingbirds. And so they would create airflow and watch how the hummingbirds responded not only to different speeds of airflow, but actually turbulent airflow. So the fundamental question was, how do hummingbirds cope with turbulent airflow? Because that's the reality oftentimes. And it's a windy day out, it's not nice, smooth flow. And we'll talk a little bit about flow and what smooth flow actually means in a physical sense. But there's a lot of turbulent flow. And you have already a little bit of a feeling, I'm sure, for what turbulent means. It's this unsteady airflow. And so the question was, how do hummingbirds respond to this? So they set up this wind tunnel, a miniature wind tunnel, in which they could control the flow, create turbulent flow, and then photograph the hummingbirds. And then on the hummingbird images, you can see a schematic image of one here, they marked different features, different aspects of the hummingbird's body and followed the movement of those points in space over time while the bird was actually feeding and getting its nectar out of that cylinder you see in the picture. Now the results were kind of amazing, I think, because not surprisingly, and here you see it in slow motion, when the airflow was smooth, the hummingbird would sit very stably and easily be able to flow, easily be able to feed. What I'm not showing here, in another study I read, the angle of the hummingbird body also changes depending on the wind direction and the wind speed, and it becomes more horizontal in a headwind and then more vertical in a tailwind. And so it can control its flight very precisely, its body angle very precisely, in order to be where it wants to be to get into that nectar. Now what happens in turbulence? So this is amazing. So the birds are able in real time, in very turbulent conditions, to be adjusting the pattern of their wings, the way their wings are moving, and adjusting their bodies, getting the food, getting the nectar that it wants. There's a beautiful hummingbird flying video that I also found from National Geographic. You see it here. It shows just the incredible just beauty, just pure aesthetic beauty of how the wings move and how well the hummingbird is able to control those wings and control its position and allows it to do these amazing things that no other bird actually can. So this is all physics, right? This is all physics, the physics of flight, the physics of airflow, the physics of muscle contraction that makes those wings move. There's all sorts of incredible physics, even at that macro scale. Then, of course, the physics of the balance and the sensing of the wind flow, all these things that these hummingbirds are able to do in real time in order to get the food that they so desperately need. So these, again, it's just another example of nature and where physics and nature come together, and the explanation is physics applied to biomedical engineering. Now, physics has to be quantified. These studies always were quantified. If you look at the original paper, they actually had plots showing the various angles of the wings and the body as a function of the wind speed and wind turbulence level, all these sorts of things. So numbers are important to us, and you can't do physics very far without numbers. You certainly can't do anything applied in physics. You might do some theoretical physics without numbers, but as soon as you start to apply it, then you're in the domain of measurements, and measurements need numbers, and so numbers end up being an important currency for us. And so as biomedical engineers, we have to be comfortable with numbers. And there's lots of different aspects to numbers. The size, obviously, of the number and the units of the number, all those things, really quite important. And I want to capture some of that importance for you today as well. With numbers and with measurements come these concepts that the first chapter in the textbook covers nicely, and that's accuracy and precision, and what we mean by those two very important terms. And here you see 4 bullseyes with arrows stuck in those bullseyes. And in each one of those cases, I want you to ask yourself, where is their accuracy and where is their precision? And if you've read the textbook, then you should be able to figure this out very quickly. So let's stop now, literally stop the video. Hopefully you stopped the video by now. Stop the video and then write down, just make a little note on a piece of paper or in your brain, whatever you want. And look at each one of those 4 cases and say, which case am I looking at in terms of accuracy and precision? Okay, stop the video. Now start the video again and you'll see some answers. So what do we have here? They should be pretty obvious. On the left is both accurate and precise. The arrows are all close together and they're close to the center. So that was an accurate shot, it was toward the middle, and it was a precise shot in that it got the same result over and over again. The second case is accurate. They're all sort of near that bullseye, but they're not very precise. They're not consistently near the bullseye. The third case, they're all bundled up very close together, but they're off the bullseye. So it's almost like a systematic error in the precision of the bow or the person using the bow. And then finally, if they're off the red, so off the bullseye and not very close together, then they're neither accurate nor precise. So keep those concepts in mind throughout your studies, arguably, and throughout your life as a biomedical engineer, because it's important to understand when it's important to be accurate and when it's important to be precise. And you can think of lots of cases like having a COVID test or a test for coronavirus, where you could think, what's better? Do I want to have precision or do I want to have accuracy? And ideally, we want to have both, but sometimes we have to trade off one against the other. Now, you know a little bit about statistics, I'm sure, and you're going to learn a lot more, trust me, in this class and subsequent classes. And one of the things that we do when we're in the lab making measurements to improve precision is what? Well, we measure more often. We measure more often, and we hope that over time those numbers converge on something and we get a distribution like you see here. And with a more precise measurement, that distribution gets narrower and narrower. So we're repeating the measurements, we're making more and more accurate measurements, and over time that distribution will get narrower. An accurate result is one that comes close to the true value. The right-hand set of histograms, and a histogram is this frequency distribution. You should know those, and you'll certainly be making those from the lab. In this case, we have the blue distribution, the red distribution, and they're both equally wide, so they have equal precision. But what do they lack? They lack accuracy because they're not in agreement with each other. So one set of measurements gave the blue distribution, one set of measurements gave the red distribution. And what's worse still, you can see here the true value is also marked in that graph, and it's even further off to the side. So these measurements had a certain consistent precision, but they didn't have very much accuracy, or as much accuracy maybe as we'd like. Now the question often is, how much is enough? How much do we like, and how much are we willing to spend to get the accuracy and precision that we really want? And those are very reasonable and sensible engineering questions, and I want to dive into one of those right now, because this is a case that comes out of absolute real life. And we're going to talk a lot about the heart and cardiovascular system in this course, so I thought I'd pick an example out of the heart. There are a number of heart illnesses, some of them you may have heard of. You'll hear about lots more through this course. One of the ones that's very important is called heart failure. And so this happens when the heart literally fails, in the sense that it fails to beat. It fails to pump. That's an important objective of the heart. That's why the heart is in our bodies. It's what the heart does for us. And so when the pumping isn't adequate, we need to worry about it. We need to be concerned. And it's a major clinical problem. There's lots we could say about it. Here you see two still images. On the left side, you see a normal looking heart. On the right side, you see a heart that has so-called dilated cardiomyopathy. What the heck does that mean? So a cardiomyopathy generally is an illness of the heart tissue or the heart structure. So it's a structural, fits in the category of structural heart disease because there's something wrong with the actual tissues, muscles of the heart itself. And that tells you that you should be able to look at that picture on the right and say, oh, that looks different from the picture on the left. You literally can see structural differences. It's a dilated cardiomyopathy because it's dilated. If you look at the volume of the left ventricle, which is the ventricle that you're looking at when you look at these pictures, strangely enough, is on the right. This is the heart as it sits in your body. So if you picture that sitting in the body, that ventricle, the one with the white arrows, that's the left ventricle. And you see that the left ventricle has nice thick walls and a fairly limited volume on the left. And on the right-hand side, those walls are thinner and the volume is larger. So that whole heart has distended or grown or dilated, hence the name dilated cardiomyopathy. Now, as I say, this is a major clinical problem, and we have some pretty cool ways that biomedical engineers have developed for evaluating the condition of the heart. This is what doctors use right now in the hospitals all around the world. One of those is ultrasound. Now, ultrasound is a form of sound, high frequency sound, that will go through tissues and will reflect off tissues, and certain tissues reflect it a different way. Now, this is a huge topic. We have a whole course dedicated to ultrasound, and I'd encourage you, if you're interested, to have a look at that course. What ultrasound does is it gives us a moving image or a movie of the heart. We can watch the heart actually beat. And so on this left image here you see, or the image you're seeing in front of you now, that's actually a normal heartbeat. And if you stare at it long enough, you can kind of see the valves flapping with our valves that control flow. We'll learn more about those. This is kind of an upside down picture in that the tip of the heart, the part that's usually at the bottom, is at the top of the image. And the bottom is where the atria are, the two upper chambers, and they're normally at the top of the heart when you see it in somebody's chest. Now the right-hand image, or this other image you're seeing right now, that's a heart that is not beating so well. And you can see that just by comparing it with the other image, that it's just not contracting very strongly. It's just not a real oomph push that you can see blood moving. Now, ultrasound is one way we can use to evaluate the condition of the heart. A modern way that also has a lot of utility but is more expensive, has downsides as well, but is equally safe and somewhat more accurate because it can be done three-dimensionally, is to use cardiac MRI. So this is magnetic resonance imaging applied to the heart. And here you see a heart beating. In fact, we can even compare what it looks like when a heart beats normally. So there you can see it's in slow motion. This is not real time. It's the nice thing about all these modalities. We can slow them down to see the details. And that's a normal heart beating. And this other movie shows you a heart that's not beating normal. You see the left ventricle is barely contracting. So this is a heart that is clearly failing. Okay, so you say, wow, that sucks to have a failing heart. I don't want to have one of those. Well, it turns out that we can modulate the heart in such a way that it helps patients who have this disease. It's a disease of the tissue. We don't know how to reverse it. There are no ways to cure it very well. In fact, oftentimes the ultimate cure is a heart transplant. So when heart failure goes truly badly, the heart transplant is really the only solution. However, I mentioned before about electrical modulation of the heart, and this is a device that does that in the extreme, and it's a defibrillator. So what this device does, and it's an implantable device, it monitors the electrical activity of the heart, not the mechanics, but the electricity, and it detects when the heart is going into a very bad rhythm. And then it shocks the heart, and it brings it back, hopefully, into a normal rhythm. And you could say, well, what does that have to do with heart failure, which is a mechanical illness? Well, it turns out that studies showed over some period of time, repeated studies, that if you use this device as sort of a monitoring device, that a heart that's failing will go into electrically abnormal rhythms that will degenerate sometimes into what's called fibrillation. That's truly uncoordinated electrical activity, which leads to uncoordinated mechanical activity. So there were a number of studies, like I say, over years, and especially this landmark study in 2002 in this very famous journal, the New England Journal of Medicine, that described an approach to prophylactically implant. So prophylactically, so this is not when people actually have had electrical abnormalities, but they have heart failure. To implant one of these devices is sort of a monitor to watch over that heart and then shock it when the heart gets into a very bad rhythm. And the quote from the paper is, "Our findings indicate that the implantation of a defibrillator improves survival," and that's an important clinical outcome metric, probably the most important one, "improves survival among patients with a myocardial infarction and a left ventricular ejection fraction of 30% or less." Okay, what does that mean? So these were patients who had a heart attack, and that's probably why their heart was failing. And they had an ejection fraction, and again, this is a term we'll come back to. This is the amount of blood that leaves the heart with every beat. So it says 30% says that if I fill a heart up with half a liter of blood, that a third of that half liter will leave the heart in a heartbeat. And 30%, that's actually not a great number. So you're all running around 50%. That's a nice normal number. 30% is a low number. And they discovered in their study of many patients with many different ejection fraction values that 30% was a good cutoff, that was where it made sense to implant these devices. What impact did this study have on the use of these devices in patients? And the impact was enormous of this study and other studies with it. What you see here is the number of implantable worldwide ICDs per year as a function of time from 1980 to 2005. Now you remember that study was in 2002. And what you see is the steady growth of the number of implantable cardiac defibrillators going in patients that peaked at around 2000, was reinforced in 2002, and has stayed pretty steady, or at least steady up until at 2005. So that shows the impact of this discovery on the number of these devices that were actually used in patients, under the assumption that it could save some patients. And the study showed that indeed patients survived longer, they didn't die as frequently, when they had one of these devices in place. So again, you'd say, why not just put one of these devices in everybody who looks risky? They have a heart attack, they have ejection fractions starting to go down, put these devices in, everything's great. But there are downsides to this. Having an implantable device is kind of a non-trivial surgery. This is a reasonably big deal. It's not a huge deal, but it's not the kind of thing you'd wish for yourself if you didn't have to have it. It's also quite costly. So it varies the cost across the world. The prices are getting a little bit better now because we're more efficient at doing it, but we're talking tens of thousands of dollars to put one of these devices in a patient. And then it has to be monitored. So the patient is kind of tied to a cardiology center, has to be checked regularly to make sure the device is functioning. Every 5 years or so, you have to take the device out and replace it because the batteries die. So this, you don't want to have a device like this if you don't need one. The second factor is that there's pain involved with one of these goes off. So when a defibrillator shocks your heart back into normal rhythm, it hurts. It just flat out hurts. And so you don't want to have that going off unless you really need it. If you need it, if it means life or death, you'll put up with that pain. But if you don't, then it's a really inconvenient thing to have to live with. And finally, recent studies have shown, this is a study from 2011, so not that long ago, that there's actually increased risk to patients who have shocks that they don't need. So if you have a device like this, it senses an abnormal rhythm, shocks you, your risk of death actually goes up. Your mortality increases. And so this is also a really important factor that makes you think, or makes the cardiologist think, do I really want to put this in this patient? Is this advised, or is this actually a bad idea? And again, we come back to that 30% number, that 30% ejection fraction, because the studies on the one hand said, yeah, there's a good trade-off at 30%. So when ejection fraction goes down to 30%, put the device in. Patients will benefit overall from it. The trick now is, how do I know what 30% looks like? How do I measure 30%? How accurately can I determine that 30%? Now, if you look at that MRI again, the one I showed you before, and you see again, if you looked at that, how would you determine 30%? And how much confidence would you have to say, No, that's 30% and maybe not 32%, because at 32% we don't put the device in. At 29% we do put the device in. How carefully and accurately, in this case, can we determine ejection fraction? And this is the job that biomedical engineers have. They have to make the devices and tell the physicians the accuracy and precision of those devices so that the physician can be confident and make good clinical decisions. So what we do as engineers plays out very directly in the lives of patients. Even though we may never see that patient, we may never have to apologize to that patient because we didn't make the device as accurate as we wanted to, or we overrated the accuracy of that device. Let's say the patient was really at 29 and our device said 33, so they don't get a defibrillator and they die maybe because of it. So these are the responsibilities we have as biomedical engineers that we don't necessarily realize on a day-to-day basis, but they're very real, they're very relevant, and numbers are important, and the confidence and accuracy of numbers are critical to what we do in our profession. So how do we indicate with numbers that accuracy, that confidence we have with them? And of course, we attach an error. We attach an estimate of the error. We don't take a single measurement, we take multiple measurements, and from those multiple measurements, we come up with a range over which we're confident. This is the world of statistics, and as I said, you're going to see a little bit this year, you're going to see a lot more next semester, about how to do that. What's the math behind those statistics that give us the power and the confidence to say something useful to the medical world, to a physician, and ultimately for them to say to their patients. And numbers get better, error gets smaller, accuracy goes up in lots of regards. Turns out that in the 1850s, there was only an approximate estimate of the height of Everest. It was only estimated to be 29,000 feet, and now we know it's 29,017 feet. And so that difference may not seem like a lot, but it suggests additional accuracy, and that accuracy has to be captured in the number. And we call the way we describe that accuracy, we capture that in the context of what we call significant figures. So significant figures are the number of digits you feel confident providing when you make a measurement. So if you make a measurement with a certain device that has, I don't know, you make a measurement with a meter stick, and it has the lines in that meter stick, then you have to look at that device and say, what's the accuracy that I think I can capture consistently with that meter stick? Is it a centimeter? Is it a millimeter? Hopefully something in that range. It's certainly not going to be smaller than a millimeter, very likely. And we have to be aware of that, and then we have to express our answers in that context. And what's really dangerous is when we start manipulating those numbers in order to find an average value, to transform them in some way, to turn them into the right units we need. It's very easy with a calculator to suddenly get a number that's this long. And then we have to think, wait a second, how accurately did I really make that measurement? And that has to be seen in the number of digits I confidently write down when I write that number down. So even when we're making a single measurement, we should have a sense of how many figures, how many of those numbers I write down are actually significant in the sense that I have some level of confidence that they mean something. So if I'm measuring, again, with a meter stick and I start putting numbers down that are 14.3725 centimeters, then I'm suggesting that I have accuracy in the range of microns, which is 10 to the minus 6 meters. You can't even see a micron. So how can you possibly suggest you have accuracy there? So this is why significant figures are important, and it's why we're going to nag you with them all semester. So I'm going to warn you right now, we are going to watch how you use numbers, how you express numbers, and one way we're going to do that is by evaluating the number of significant digits that you express in the numbers you write down from a lab exercise, from solving a problem in a homework assignment, and we're going to actually try and be developing you some feeling for this, some consistency of this. So be warned, significant numbers are important. And there's a whole moderately well-developed theory, I would say, that describes what happens when you start combining numbers and manipulating numbers. The bottom line is that it all makes things worse. So if you take two numbers and combine them, then the accuracy of the sum is lower than the accuracy, or your confidence is lower of the sum than it was of the individual numbers. So it's really a bad deal. And we're not going to go into all the details of that. Hopefully you've seen some of that in other courses, have some notion of how errors propagate through calculations. But at the end of the day, we're going to focus on common sense. So if you start with a measurement that has a certain accuracy, no matter what you do along the way with those numbers, the final result should reflect that accuracy in some way that indicates your confidence in those original measurements. So that's the thing to really keep in mind when you're thinking about how many digits are meaningful. So we literally, in one of the lab experiments where we measured the weight of a can, an empty can, the number that the student delivered on their lab report, and I'm reading it here, is 0.78333 foot-pounds. That's the weight of that can. Now that suggests 1, 2, 3, 4, 5 significant digits of accuracy, and that's obviously rubbish. Those last 3, 4, whatever number of digits have no meaning whatsoever. There's no confidence in those digits, so why write them down? You're creating accuracy you don't really have. So that's enough said. We'll come back to practical cases in the homeworks. Now, of course, numbers need units, and you should get used to the units that we have, and we're a scientific community. You're in the world of science, and so you have to use scientific numbers. And these are numbers that are not necessarily the terms that you'd hear talking about. You'd not necessarily even weight in pounds, and certainly not length in inches. But the scientific, the SI units that the world has agreed that are going to be consistent across the world for use in scientific communication. So you're just going to have to get used to those numbers. Certainly you have to transfer them, translate them using various factors, and we'll give you some exercises to practice converting from one system to the other. And you should just be comfortable with this. This is not hard math. You just have to think through, what you're trying to do. And then we also want you to get used to the prefixes that make sense for these numbers. So there's no point in expressing my height in terms of microns. A micron is 10 to the minus 6 meters. Similarly, there's no sense in expressing the size of a virus in terms of meters, because you'll end up with this crazy exponent. So what we want to do is find the right prefix to bring the numbers down into the range that makes sense. So we're going to encourage you to use millimeters, microns, centimeters, whatever they seem useful for the size of the object in the case of a length measurement or the mass of that object. So we're going to encourage you to use those prefixes and get used to them and memorize them if you haven't already, if you didn't get this in grade school. This is not new stuff for you mostly, I hope. Now, connected to all that of numbers and units and confidence in those numbers is we want to develop in you a certain sense of what are sensible sizes of numbers. So what's a sensible number for a blood pressure? And what's the normal units for blood pressure? They're going to be different from the units of pressure in your car tires or in your bicycle tires or in other situations where pressure matters. And we as biomedical engineers have to learn the numbers, the units, and the sensible values that arise in medicine, in our bodies, in animal bodies, in living systems. And you're going to get lots of those throughout the semester. And here's just some simple examples that you may already know and you should start to develop. And you could argue you're going to memorize these. Hopefully you'll be dealing with them enough they won't feel like a memorization exercise. But you should really know, for example, or should have some sense of, first of all, where a millimeter of mercury comes from as a unit. It's a very easy unit to picture because it's the height of the column of mercury that a certain amount of pressure will sustain, will support. And again, you can look that up anywhere if you need a review of that. But you should know that our blood pressure, for example, is what? What's a typical blood pressure? Should arguably have a sense of that. Is 300 over 20 a good range of blood pressures? And why do I have two numbers in the first place? Well, you're going to learn more about this, but there's a systolic blood pressure. That's the blood pressure when the heart's contracting actively. And then there's another pressure when the heart's relaxed. And that pressure in the heart has range of values. In the vascular system, in the aorta and the arteries, it has another value. That value goes down as we move through the cardiovascular system. And you'll learn all about that, especially in the context of the major project. So you should develop a certain sense of what are the range of numbers and what are the units that we're going to use. So look up what a normal pressure would be for a healthy human being and try and keep that number in your head. That's a number you use throughout this semester and probably a lot of your life. That's a very reasonable number. And you may already know it, even for yourselves, if you've ever had your blood pressure taken in any kind of checkup you ever had done. Heart rate numbers. Of course, we should have a sense of what the range of heart rate numbers are. We should know what our body temperature is supposed to be, and we should know it in Celsius and centigrade degrees, not just in Fahrenheit degrees. Again, temperature is measured in Celsius in a scientific setting, and in most of the world, this is how even doctors in day-to-day life goes on. People know that 30 degrees outside is a pretty hot day. They don't have to think and convert in terms of Fahrenheit degrees because they just have a feeling for those units. And you have to develop a certain feeling for those units as well because they're relevant to our field and to medicine, and that's the world that we live in. So I think that'll get you started. I'm going to assume that you will go through this video, do the other parts of the reading, read the chapter, and that with all that information, you'll be in good shape to handle the reading quiz, which you should do after you've completed the video and after you've read the chapters. Thanks. See you soon.